everyone, welcome back. This is lesson 9.5, functions and their inverses. The objectives for today, you're going to be able to determine whether the inverse of a function is a function, and you're going to be able to write rules for the inverses of functions. Your vocabulary for today is one-to-one function. In lesson 7.2, you learned that the inverse of a function f of x undoes f of x. Its graph is a reflection across the line y equals x, and the inverse may or may not be a function. So let's just put that in picture form here. If I have a graph that, let's say it looks something like that, the line y equals x is actually this line right here. And the reflection across it would be the inverse. So my inverse graph would look something like that. It would reflect across that line y equals x. Recall that the vertical line test can help you determine whether a relation is a function. So let's take a look at that. Remember, we had our function, our graph. Let's say it's a parabola in this case. And we used our vertical line test to make sure that every x was only paired with one y. And in this case, there's only one y for every x. And so that told us that this was a function, okay, the vertical line test. Similarly, the horizontal line test can help you determine whether the inverse of a function is also a function. So let's talk about that next. If any horizontal line passes through more than one point on the graph of a relation, the inverse relation is not a function. So let's take a look at these two examples. The first example, if we do a horizontal line test, we're checking to see for every y, is there only one x that matches with this? So here's a y, only one x. So you can see that our vertical line test, for every y, there's only one x. It only crosses one place. All right, so because of that, we can think about what our inverse would look like. And our inverse, remember, reflects across this line, y equals x, okay? So if I were to write the inverse of this, my new function would look something like this, all right? And this test, this new graph, actually does pass the vertical line test, so we know that it is a function, okay? Let's look at this next picture. On the next graph, when we do the horizontal line test, notice that there is, for every y, there's actually two x's. This y, this x, and this x, okay? So every y has two x's. And even though the original graph, which we see does pass the vertical line test, it does not pass a vertical test. It has two x's for every y. And so if we were to reflect it across the y equals x axis, here it is, our new graph would actually look something like this. Let's see if I can do that. Something like that. All right, and notice if we do the vertical line test to find out if that is a function, we see that it actually does not pass the vertical line test because now for every x, there's actually two y's. All right, so we can't have that and still be a function. So that's a really easy way to tell. So if the first graph does not pass the horizontal line test, then the inverse is not going to be a function. Let's take a look at this first example. Use the horizontal line test to determine whether the inverse of the blue relation is a function. So all we have to do is we're going to just draw our lines, and notice that there's for every y, there is only one x. All right, so it actually passes the horizontal line test for the blue. All right. And so once we do that, we can see the inverse is a function because no horizontal line passes through 2 points on the graph. All right, next. In this example, we're going to try the red one now. So now we're going to look at this red graph. All right, so let's do the horizontal line test on the red graph. So it's okay here, it's okay here, it's okay here, but look what happens when I get up here. I have each y, I have several points that pass through, so I have several x's. So that tells us that it does not pass the horizontal line test. Now notice, I'm going to erase this for a second so you can notice. Notice that the red graph actually does pass the vertical test. When I do a vertical test, we see that it's a function, but because it doesn't pass this horizontal test, okay, it doesn't pass here, it tells us that the inverse will not be a function, all right? So the inverse is not a function because the horizontal line passes through more than one point on the graph. All right, try this one on your own. Turn your video off and give it a try real quick. Okay, you were supposed to use the horizontal line test to determine whether the inverse of the relation is a function. So when we do that, we see the graph only touches the line once. So every x is paired with only one y, so that tells us that the inverse is a function because no horizontal line passes through 2 points on the graph. All right, so recall from lesson 7.2 that to write the rule for the inverse of a function, you can exchange the x and y and solve the equation for y. Because the value of x and y are switched, the domain of the function will be the range of its inverse and vice versa. Okay, we did this before, so this shouldn't be too hard for you. Okay, let's try this example. It says find the inverse of this equation and then determine whether it is a function and state its domain and range. So you could just graph this into your calculator. I've already done it for you. And when we do, we see this graph. We can use the horizontal line test, and when we do, we can see that it shows that the inverse is going to be a function because for every y, there's only one x. All right, so the horizontal line test tells us that when the inverse will indeed be a function. We also need to note the domain. That's our x's. Our x's are going to be all real numbers because they just keep on going, and our y's will also be all real numbers. All right, so the second part of our problem, we need to find the inverse. So let's recall what our original equation was. It was f of x equals x plus 1. All right, so remember to find the inverse, we're going to call this y equals x plus 1. And now to find the inverse, we're going to switch our x's and y's. So we're going to rewrite it to say x equals cube of y plus 1. All right, so let's go from there. So first we want to rewrite our function using y instead of f of x. And then we're going to switch our x and y's in the equation. All right, now notice that my index was 3. All right, so if I cube both sides, I end up getting rid of this radical sign. And so when I simplify it, I get x to the third equals y plus 1. Now remember, our job is to solve for y. So I want to isolate my y by itself, so I'm going to subtract, I'm going to subtract 1 from both sides, and then they rewrote it to be x to the third minus 1, and so my y is isolated. All right, so because we found out at the beginning that the inverse would be a function, the inverse, here is our inverse function now, and let's talk about the domain and range about that. So the domain of the inverse is the range, the original range, all right, and now the range of is the domain. Okay, so those two things just switch. And we can take a look at that in the calculator. If you graph both of these two things, put them in y1 and y2, and you could also have your y equals x for your third one, and you will see that it reflects across that. And we can also see that the domain of each of these two, here's our original one and our new one, the domain is still all real numbers, and our range is still all real numbers. All right, so try this one on your own. Turn your video off and give it a try. All right, so on this problem, you're to determine whether it's a function and state its domain and range. So we have x cubed minus 2, so let's just take a look at that in the calculator. And when we do a horizontal line test on this, we see that the inverse is going to be a function, okay? The inverse is going to be a function. We also want to take note that the domain and the range are both all real numbers, all right? So the x's and y's are going to just go on infinitely. All right, the second step you need to do is find the inverse. Okay, so let's rewrite the function and use y instead of our f of x. So we're going to say y equals x cubed minus 2. Now remember, next thing we're going to do is switch the x and y's. And now once I do that, now I'm going to go back and solve for y. So first of all, let's add 2 to both sides. So I end up with x plus 2 equals y cubed. Now, how do I get that to be y by itself? Well, remember, if I have a cube here, I can get rid of it by cubing it, doing the cube root of both sides. And by doing that, I end up with y equals the cube root of x plus 2. Now, remember, we knew that the inverse is a function, okay? So here's our inverse function. The domain of the inverse is still going to be the range, which our range we said was all real numbers. And the range is going to be the domain of the original f of x, which was also all real numbers. Again, you can put it into your calculator. They didn't write it on here, but you could just put an x for y3, and that'll give us this line here. All right, and once again, we see that this is a reflection across that y equals x-axis, and we can see that the domain and range are both all real numbers. You have seen that the inverses of functions are not necessarily functions. When both a relation and its inverse are functions, the relation is called a one-to-one function. In a one-to-one function, each y value is paired with exactly one x value. You can use composition of functions to verify that two functions are inverses, because inverse functions undo each other. When you compose two inverses, the result is the input value x. All right, so let's see what that actually means. All right, here it is in words. If the composition of two functions equal the input value, the functions are inverses. So let's read this. This says, if f of g of x equals g of f of x, and they both equal x, then f of x and g of x are inverse functions. All right, and here's an example. If f of x is 3x and g of x is 1/3 x, we could say f of g of x, so that would say 3 times g of x, which was 1/3 x, equals x, because these cancel out, so that just equals x. And when we do it the other way, g of f of x, so that's 1/3 times 3x. Again, the 3's cancel out and we get x. So we know that the composition, that these two are inverses by doing the composition. All right, so let's do an example now. It says determine by composition whether each pair of functions are inverses. So the first thing we want to do is find the composition f of g of x. So what that tells me to do is take what's in f, and I'm going to find g of x. So everywhere there's an x in my f of x, I'm going to put this whole piece into here. Okay, so now once I've done that, I'm going to distribute this 3, so that's going to leave me with just x plus 3 and then the minus 1. All right, so I end up with f of g of x equals x plus 2. All right, well, let's think about what our chart told us a minute ago. Okay, so because f of g of x was not equal to x, it was actually equal to x plus 2. F and g are not inverses, all right? So there's no need for us to do any more work. There's no need to check g of f of x. And we can actually graph both of these, and the graphs are not symmetric about the line y equals x. So here's our line y equals x. And these two lines are not symmetric about that. So that automatically also tells us that f and g were not inverses. Okay, let's do another example like this. So we're going to determine whether the functions are inverses, and they've already started off by telling us that x can't be 1 or 0, because if it was, then our functions would be undefined, and we don't want to have that. So they're just letting us know that everything is defined. And so the first thing we want to do is go ahead and find the compositions of f of g of x, and then we're going to find the composition of g of f of x. So let's remember how to do that. We're going to take f of everything that's in g of x. So here's what's in g of x, and I'm just going to replace it into my x here. So when I do that, it looks like this. And you can see 1 minus 1 is 0, so we end up with just 1 over x. And then remember how to solve this. We just multiply by the reciprocal on the top and multiply by the reciprocal on the bottom, and we just end up with x. Yay, that's the first step to get. And so we're glad about that, because that is the first step in finding out if it's an inverse, is if it equals x. So now let's see if g of f of x. So when we do g of f of x, what we're going to do this time, just erase that, we're going to take everything that's in f of x and put it into the x's of g. So here's my f of x, and I'm going to replace it into this x. So when I do that, again, I end up with it equals x, okay? So that is, now that we see that the x's equal x, we know that they are inverses. So because f of g of x is equal to g of f of x, for all x but 0 and 1, f and g are inverses. And the great thing about math is we can always go back and check by putting these two functions into your calculator and graphing it. And when you see our equation, our original one looks like this, and the inverse is over here, going like this and this, and they do reflect across the line y equals x at all places but 0 and 1. All right, so try this one on your own. See how you do. All right, let's see if you did it okay. So the first thing you want to do is you're going to find the composition of f of g of x and the composition of g of f of x. So what that tells me is the first time we're going to take everything in g of x and we're going to place it into f of x, where the x is, all right? And so once you do that, you should have come out with x. So that's a good step. So now we're going to try it the other way around. This time when we do g of f of x, we're going to take everything that's in f of x and put it inside the x that's in g, okay? So if you're not sure of that, turn your video off and just study it for a few minutes. And then when you actually multiply it all out and solve it, we end up with x. They both equal x, and if they both equal x, that tells us that they are inverses. And again, you can check and you see that they are symmetric across the y equals x and for all x's. All right, here's one for you to try on your own again. So turn off your video and see if you can find out if these are inverses of each other. All right, so the first thing you should have done was to find the compositions of f of g of x and then g of f of x. And the way we do that, let's do the first one first. We're going to take everything that's in g of x and place it into the x in our f of x. So we're going to substitute. And once I do that, my equation looks like this. Now be really careful when you see this. Don't forget that what that really means is a problem like this, times the square root of x minus 5. Now you can't just square each of those, you have to actually FOIL it. So that's going to be x squared, this is going to be minus 5 square root of x, and then another minus 5 square root of x, and then plus 25. Okay, that last one. So you're actually going to end up with x squared minus 10x, like this, plus 25, and then plus our extra 5, and it ends up like that. And then we simplify this part, and there we have f of g of x equals x minus 10 square root of x plus 30. That is not equal to x. So what that tells us is, Because f of g of x is not equal to x, f and g are not inverses. So there's no need to check for g of f of x. And you could also put it in your calculator and see, but for your test, I will want to see your calculations on paper. I don't want to just see a graph. All right, here's a quick lesson quiz. We're at the end of the lesson now, so turn your video off and try this one and make sure you understand it. If you don't, you can go back to the beginning of the video and check it. It says use the horizontal line test to determine whether the inverse of each relation is a function. Okay, so when you look at A, if it passes the horizontal test, which it does, we know that that function, A, is going to be a function. The inverse is also going to be a function. But let's look at the section B here. Notice it does not pass the vertical line test right there. So the inverse of B is not going to be a function. So A is yes and B is no. Okay, turn the video off and try this one on your own. All right, so I hope that you noticed that the first thing it says to do is find the inverse. So let's go ahead and remember to take our f of x and change that to y, and y equals x squared minus 4. Now to find the inverse, we exchange our x for our y, and then we solve for y. So we're going to add 4 to both sides. We end up with y squared equals x plus 4. And now to get rid of our square here, we're going to square root both sides and end up with y equals plus or minus square root of x plus 4. And then to rewrite it as in function form, x negative 1, that tells us it's the inverse, equals plus or minus square root of x plus 4. So there we have our inverse. And the next thing that it tells us to do is determine whether it is a function, and then we need to state its domain and range. So let's decide whether it is a function. So let's take our original problem, f of x equals x squared plus 4 or minus 4. So this is a pretty easy picture to draw, okay, because we know the parent function, x squared, and this says just take the parent function and translate it down 4 units. So we're going to go down 4 units, and now we just have our regular parent function like this. All right, and now we need to determine if the inverse is going to be a function. Well, to determine that, we need to do the horizontal line test, and notice that the horizontal line test, for every y, there's actually 2 x's. All right, every y has 2 x's, so that means that this is not going to be a function. All right, and the final thing that we need to do is state the domain and range. So let's go back and let's just clean all this up for a second. Let's look at our domain and range again. All right, so for our original function, it was down here like this. And our domain is going to be all real numbers. Domain is going to be all the real numbers. But the range, notice, the range can't be any less than negative 4. So it's going to be y such that y is greater than or equal to negative 4. All right, so now we have to talk about the inverse. So let's talk about what our inverse is going to look like. Our inverse, remember, is going to be a reflection across this line here. Okay, our y equals x line. So our new inverse parabola is actually going to be something more like this. All right, this is what our new inverse form is going to look like, and this is actually at x equals negative 4. So here we can see now our y's, our range is going to be up or down anything. So now our range is going to be y is all real numbers, okay? But our domain now is actually going to be the x such that x is greater than or equal to negative 4. So all of my x's have to be greater than or equal to negative 4. So notice that the domain switched places with the range, and the range switched places with the domain. The domain is now the range. Okay, let me rewrite that to make domain. Okay, so here it is written out, our inverse function, and it is not a function, and the domain is now x has to be greater than or equal to -4, and the range is all real numbers. And the last quiz for you to try on your own. Turn your video off and try this one. All right, so this one says to determine by composition whether f of x equals all of that are inverses and x cannot equal 0. And when you work it out, you should have found that yes, they both equal x, and so yes, they are inverses. And I'm not going to go through that with you, but if you need more help, you can go back and look at the video again. All right, well, that's all that we have for this lesson. I hope you guys have a great day, and I will see you soon.